Okay, great. People remember the primal objective function that we had for SVMs. So this is a primal objective function we had for SVMs. So one way of thinking about it is to say that I am going to write it the following way. I mean some jugglery. So the alphas I have replaced it with a lambda here, okay, and well you know xi transpose beta plus beta naught is actually f, right, f of xi, right. So I have written f of or s should be f of xi, sorry, yeah, that is f of xi, and then essentially the same objective function except for this plus thingy here. So what does a plus thingy mean? So it means that I will count this, okay, only whenever this is positive, right. Whenever it is negative I will treat it as 0. Does that make sense? I will count this only whenever it is positive, whenever it is negative I will make it, I will consider it as 0. So that is what the plus term here indicates. Huh? They went into lambdas. I mean I kind of redid this thing, right. So I divided everything by some factor of alphas and moved it to lambda there, okay. Right. So if you stop a minute, this should look familiar to you. What does it look like? Ridge regression, right, ridge regression. So you have a loss function, okay, and you have a penalty term, right. Doesn't it look like that? So far we have been talking about norm beta squared as being the objective function that you are trying to minimize, and the other thing as constraints, right, and then we wrote the Lagrangian, and then we got the constraints into the objective function. So now I am saying you can think of another way of writing the objective function, which is to say that there is this loss function, right, which is accounted whenever it is negative, right. So now your goal is to minimize this. Right. So how will this loss function look like? Right. So when y of x is 1, after that it will be 0. Right, that loss function, I am only talking about the loss function, not about the penalty term, right. But till y f x becomes 1, it is going to be a linear function, right, you can see that, right, it is just 1 minus y f x, so it is going to be a linear function of y f x, right, is it clear? Right. So this kind of a loss function where this is like a door or a book opening on a hinge, right. If you think about it, this is like two flaps of a book or a door, right, and it is opening on the hinge which is here, right. So it is also called right. So sometimes if you have read about SVMs elsewhere, you might have heard that the SVMs minimize hinge loss, right. So this is exactly what we are doing here. So the hinge loss actually arises from the constraints that we are imposing on the SVM, right. But if you think about it, where did the constraints come from? Why were the constraints imposed? What is the semantics of the constraint? I do not want you to get, yeah, well, what was right, we wanted to make sure that they are correct and a certain distance away, right, that is the reason for this. So in effect the constraints were enforcing the correctness of the solution, right, and what the objective function originally was enforcing was essentially the robustness of the solution. How far away are you from the hyperplane, right, the constraints were making sure that you are on the right side of the hyperplane, right, if you think about it, right. So in effect the constraints are an important part of what you are trying to optimize. It is just not the distance from the hyperplane that matters, but it also matters that you should be on the right side of the hyperplane, right. So the putting it as a hinge loss makes that explicit, right. I am saying okay, this is the loss function I am interested in, right. So that essentially tells me okay, I am interested in the correctness, I want to make sure that all my data points are correctly classified, okay, and the penalty tells me okay, make sure it is a small norm solution, right. This essentially becomes like ridge regression, okay, make sure that the squared loss is as little as possible, at the same time make sure that the norm of the solution is also small, right. So that is what we did, right, we enforced the L2 norm in the ridge regression case and we are doing the same thing in the SVM case, okay. Does it make sense? Now we can ask interesting questions like okay, if I replace this with some other norm penalty, what will happen? Can you do L1 regularized SVMs? No, that was regression. So L1 regularized regression was lasso. Can you do like lasso like regularization for SVMs? So instead of beta squared, if you put beta, what happens? What do you think will happen? You will have a much harder optimization problem on your hand, but it is actually a valid thing, right. So what it will try to do, if you remember we talked about this in lasso, I mean I did it in a admittedly a little hand wavy fashion, but we talked about how it will enforce sparsity, right. We said it will try to make as many coefficients 0 as possible, right. So in this case what do you think will happen if I put norm? Can it enforce sparsity? Will it reduce the number of support vectors? Does that enforce sparsity? Think about it. What is that? Right, squared loss is actually like this, okay. So if you think about it, it's a little weird, right. So if you are to this side, you are actually correct, right, but the farther away you are from the hyperplane, on the right hand side also you still contribute to the loss because of the squared error function, right. Whether you are on the right side or the wrong side of the hyperplane, you still contribute to the loss, okay. So that is why sometimes the squared error function is not the ideal thing to minimize, right. So the hinge loss more often than not gives you a much better solution than optimizing squared error, right. So what will the squared error be? right. So that is what the squared loss function is. Okay. So normally you are used to seeing this as y minus f of x the whole squared, but I have written it as 1 minus y f of x. That is also fine, because if it is correct, y f of x will be 1 all the time, right. So right. So what is the actual loss function that you want? This is fine. That is the actual loss function you want, right. What is the loss function called? 0 1, right. 0 1 is what you really want, right. It should be 0 if it is correct, and it should be 1 if it is incorrect, right. 0 1 is what you really want, and a lot of this is just like a segue, right. It is not really, I am not going to test you or anything on it, just for your interest. A lot of work in theory in machine learning goes into showing that, hey, if you optimize some other loss function, okay, will you end up with the same solution as if you optimize the 0 1 loss, right. So if you take the 0 1 loss, I try to find a solution for it, right. I am trying to find the beta that gives me the smallest possible 0 1 loss, right. Is the smallest possible 0 1 loss 0?
No, depends on the data.
Depends on the and
Linearly separable or not?
yeah. So there is 2 points to it, right. Depends on the data, and you said linearly separable, but why? Because you chose to use a linear classifier, right. So depending on what family of classifiers you choose and the data, okay, the minimum 0 1 loss could be 0 or it could be something higher, right. So when I say minimize the 0 1 loss, I mean whatever is the minimum possible achievable given the data distribution and the class of the class of classifiers or the family of classifiers you have chosen. Given that, what is the minimum achievable? Will you be somewhere close to that if I minimize a different loss function, right. So that is an interesting question to ask, right. So I can arbitrarily come up with other loss functions. I can come up with hinge loss, I take squared loss. So if I minimize hinge loss or squared loss, will I get the same solution as I would have gotten if I had minimized 0 1 loss, right. So that is something people do think about, right. So we did look at one other loss function, which is the, I guess it was something like that. So that is what we minimized actually in the logistic regression case, even though we did not write it out explicitly as a loss function, right. So if you think about it, right, this is what we actually minimized in the logistic regression case also. We are trying to, what were we trying to do? What did we do in the logistic regression case? What did we do to estimate parameters? We did maximum likelihood, right. So we made some assumptions about the distribution, and then we tried to maximize the likelihood and so on and so forth, right. So if you work through that, you can, if you write it out as a loss function, it turns out that this is what you are trying to, so you can see that this never goes to 0, right. This is going to go like this, okay, but then you can still think of minimizing that. So that is just an aside, you do not have to worry about the logistic loss function right now, we will come back to that later, right.